Hi everyone, thank you. My name is Jean-Christophe, or JC, and today I'm going to talk about scikit-build-core, a new build backend for building wheels. First, who am I? I work at Kitware in our North Carolina office. I am the developer of 3D Slicer, a medical imaging application. I'm also the maintainer of few Python packages, scikit-build, scikit-build-core, CMake, Ninja, and also the maintainer of the CMake-based Python build system to build CPython on multiple platforms, and also the maintainer with my colleague Matt of DocCross, a collection of Docker images to more easily cross-compile any project. The goal of this talk, we're going to introduce scikit-build-core. We're going to look how it impacts the distribution and the building of wheels. We're going to see how it simplifies building C, C++, Python, Fortran, Cython, and Fortran project. Look at some of the key features and review some of the impact on real-world projects. More specifically, we're going to look at the evolution of Python packaging, the importance of build system, overview of scikit-build-core, one specific example centered around PyBind 11, some of the key features like override, dynamic metadata, some statistics, and then look at the next steps. History of packaging. We have to go back way back, and at the time of Python 1.6, around year 2000, like 25 years ago, this utils was introduced. Not sure if you are all familiar with it. That came with some challenge in terms of distribution, and in terms of like modularizing your build. Then around that time, we started to see the rise of some distribution, like the Info distribution, Conda distribution. And then 10 years later, things got a bit better. We started to see the formalization of what we call now the Python wheels, but it didn't used to be like that. Basically a zip file with a specific way of organizing the information. Setup tools became the de facto standard. At that time, we had disutils, disutils2, PBR, a lot of different way of packaging and organizing your distribution. pip hasn't always been the standard. We had also easy install, and then pip became well accepted. And then later on, with Python 2.7.9, pip got distributed alongside Python and became available out of the shelf. And then in 2014, scikit-build Classic came, and that started at the sprint in 2014 with my colleague Matt, Anthony Skopats, Mike Saran, and few other one. And that was a bit of a crazy idea to sort of bridge the classic setups, to bridge setup tools with CMake. And then later on, we are like, oh, let's rename it to scikit-build. PyCMake was a bit less scikit-centric in a way, and we wanted something more implicated with the community. And then as of today, scikit-build Classic is getting close to 800,000 downloads per month. But scikit-build Classic got some limitation. You still had the setup.py. You had to sort of mock around, and it was not like built on some of the more modern standard. And then to help address some of the limitation, we had what we call the PEP revolution. And if you're familiar with the PEP 517, PEP 518, and the idea was to sort of decouple what we call the build front end and the build back end to enable the implementation of different mechanisms to generate a wheel. And we needed to take advantage of that, and that's why then later on we introduced scikit-build-core, because scikit-build Classic was sort of we were hacking around and we are not taking advantage of this PEP. And now let's do a little bit retrospective of before PEP 517. Everything was simple at that time. You had like your setup.py, and you could like build a C extension. It looked simple, but in fact we needed more. We needed a third-party dependency. We needed compiler-specific flags, parallel compile, customization of the wheel bidding process, Fortran, other compiler, IDE support, and whatnot. And that was lacking. And by integrating CMake with setup tools, we could bring some of the advantage of CMake to describe our build system, to build our project, and address this aspect. But as I mentioned earlier, these extending setup tools was challenging. We had to sort of like monkey patch, hack around, and it was really fragile and brittle because each time we had a new version of setup tools, we had to be really clever to keep the Surface API simple while keeping existing project working with the scikit-build classic. But then, to address that, we introduced scikit-build-core, and scikit-build-core take advantage of the modern standard, which consists in decoupling the build backend and the build frontend. And that way we could completely get rid of setup tools and not have to describe our build system with Python code, which brings its own challenge in terms of maintenance. And Henry Schreiner, who is one of the lead core developer of the scikit app that we saw this morning, discovered scikit-build classic a few years ago, started to contribute, and then he was like, hey, let's work on the next generation. And then we applied for some NSF funding. We got that NSF funding, and then we started to work on the scikit-build-core, and that was a great progress, and that showcased the. Back in 2014, we built the boat. We helped sort of set up the direction, and then we enabled others to join us. And now I sort of stepped down from being like the main pilot of the boat, and Henry sort of like making things happen in the next generation. Now let's review from the big picture perspective. That diagram is a bit complex, but what do we have here? We have the developer on the top left, and we have the user on the top right. And we're going to review some of the terminology. On the top left, we have like our source files, py file, C++ file, C file, the pyproject.toml. On the bottom left, we have conda and pypy, and what we want is to streamline the path from the source file to the wheel, and then we have the build frontend. The build frontend is basically like pip is one of the build frontend, or the small tools called build. And then we ask build or generate the wheel, and then the build backend is configured, and we describe that in the pyproject.toml, and that build backend then is in charge of like calling CMake, generating the Visual Studio file or Make file or Ninja file and whatnot. And these files will be responsible for invoking the linker, the compiler, and for example, Clang, GCC, MSVC on Windows. And then we can create these like shared libraries. We can copy the right file in the right location. And then all of that respecting the wheel format that was introduced back in 2013. And then after that, there's a bit of post-processing to make sure the wheel is like follow some of is standardized, and the symbols are like correct, and here are the name of some of the tools that are automatically invoked. And then we get our wheels, and the wheels can be uploaded to PyPy, or we can also generate packages that are compliant with Conda. And similarly, we need also to generate a source distribution to enable build on platform that wouldn't be supported by default. And yeah, that's sort of like the big picture here. And now let's look at an example. We're going to look at the main CPP file, the pyproject.toml, and the CMake list. And to come back to the previous slide, these are the files that are written by the developer, and we're going to look at these files. Here we have a really, really simple example, main.cpp. We are describing a function that's computing the square of a number and using pybind11, a few lines of C++ code. And the link to look at that example at the bottom of the slide. Every slide have a link to the documentation or a link to the example. And then after we write the source file, we need to specify, we need to describe our project. And here it's just like some of the relevant metadata. I skipped, for the sake of space, I skipped some of the configuration of the linter tool and whatnot. But that example in itself is sufficient to build a wheel that will be published. We have the name of the project, the version, and then here we specify that we require scikit-build-core build-backend, pybind11, and then we describe how to get access to the function for the build-backend, and that's it. And then you can do python-m build dot, and then you are building the wheel and the source distribution. But under the hood, by leveraging the build backend, it will make sure that everything else you need is available. And it will call CMake, generate the make file on on Linux, or the Ninja file, or the Visual Studio file. The CMake file in itself, we specify the version of CMake we are working with. We have the name of the project. And here we're going to discover pybind11 provide us some nice functionality to create our module. And here we do a find package of pybind11. And then we add the module, we install the target, and that's all you need. And then you may have some question, okay, how does CMake can find pybind11? And I'm going to cover that in the innovative feature later on. But these are the three files you need to have to describe your project and being able to build it. And with that, it will be you will have a wheel available on all the platform. Now, scikit-build-core come with powerful configuration systems. And here, this is, for example, a set an example of some of the common options you could set. You can describe what is the minimum version, because we introduce new version of scikit-build, and we deprecate some of the options. And here you can mention like what is the minimum version, and that allows us to nicely warn you if you are using old functionality, or in some situation if we introduce a modified behavior, we can deal with that based on the minimum version. You can change verbosity. Here for the last line, we are that's to enable us to work around a bug with the older pip version that we are not expanding properly the macOS tag. Or to be able to build wheel that will work with older version of pip. Now let's review some of the features. I mentioned we need a CMake and Ninja. We could specify CMake and Ninja in the build dependency, but the challenge is that in some situation you already have CMake and Ninja on the system. It means you don't want to explicitly list that in the build dependency. You want the build backend to be smart enough and check, do I have the corresponding version on my system? And we can make that happen thanks to the PEP 5.17, which allows us to dynamically update the build dependency. The build backend can update the build dependency. It means what we do is that we can specify in the pyproject.toml what is the minimum version, and then if the build backend finds that minimum version on the system, it will not download CMake, and it will just use the one that's available on your system. Same thing with Ninja. Now, one word is that if you are not familiar with Ninja, Ninja is like Make, but it was developed by Google a few years ago as a dumber version of Make that's much faster. It means like the no-op build, even if you have like thousands and thousands of source files, is like almost instant. Whereas Makefile was taking a lot of time just to like parse all the different Makefile. I mean, Ninja is really fast now. It's cross-platform. Mac OS, Ninja, Windows, and it's gonna speed up your incremental build on your project if you have a large amount of files, and that's what we use by default. And And also because in some situation, for example, if you build for WebAssembly, we don't have to use CMake. We use a different toolchain. It means there's no need to specify CMake in your build dependency, and that's why it's interesting to leverage that feature. One word, like the CMake wheel is downloaded like 6.5 million times a month, and the Ninja wheels close to 10 million times a month in itself. Another really interesting feature is integration with external packages. And earlier, I talked about the Pybind 11, and when you have the find package Pybind 11, and how is that happening? The project called Pybind 11 that's published on PyPy expose an entry point, and that entry point, let's just assume it's called like CMake.prefix, is discoverable by scikit-build-core itself. It means each package that exposes that entry point, they will be discovered, and we will expand the CMake prefix path with the path of all this project. That way, if in your project you do a find package name of the project, it will be discovered automatically. It means we have a way to build this interdependency between projects so that they are discoverable easily without hard coding any location. Now another important feature when you development is what we had like the -e mode in PIP, like the editable mode. It means you want to be able to modify your source file in your source tree and being able to like run your test easily. And to support the editable mode, there's two ways. There's the default mode is the automatically detect change and copy the file into the corresponding build tree for the platform you're targeting. It means if you have different, you're working on different build of your wheel, like with different flag, you can easily have different build tree, you modify your source files, and then you can like test things. And we also support the traditional in-place mode where we will build the artifact in your source tree, and in some situation that will be helpful. And the pros, the cons of that approach is that you cannot test different build of your wheels at the same time because you have everything in your source tree. Other interesting feature, the dynamic metadata, and that allows us to dynamically set the version, the build dependency, any of the metadata in your project with a system of plugin. And we provide some plugin for and some adapter, some wrapper, for example, for the one for setup tools SCM, which allow us to extract the version from your source tree, one for regex, one for README, for the fancy PyPy README plugin from Hatch. And you can also have like in-tree plugin. We are also working on a draft PEP to make that part of the standard in Python. This is still a work in progress. In the meantime, we support that in scikit-build itself. But what we are envisioning is to have plugins written for Hatch, for Poetry, and any other plugin to be used by any backend, and then you don't have to reinvent the wheel, no pun intended. Other feature is file generation. Here is a simple example of what you can do. Here we have like the version file we want to generate, and then the template, and the version between the $ bracket version is like the actual version that's specified in your metadata. This one is interesting, is what we call the override, and depending on the situation, depending on the state of your system, you may want to have different requirements. You may want to set different environment variable. You may want to also set different environment variable based on the state of your build. Are you building a wheel? Are you building a source distribution? And then we have a powerful system that allows us to combine if, to do or, to do and, to update the environment, to append to the environment, to override the environment. All of that with a declarative language. Now let's go in under the hood, and scikit-build itself has more than 40 different options. All these options are described with a JSON schema that's published on the schema store. That's also discoverable by your ID to enable auto-completion when you write your PyProject.toml. And we support also passing this option, hard-coding them in the PyProject.toml, or getting them from the command line through pip or through build or through environment variable. And under the hood, to streamline the maintenance, we are using data class in Python. When you write plugin, I mentioned earlier we have like the regex plugin and we have like the fancy README plugin. You could write plugins that are also taking advantage of the CMake file API. That's a bit in the weed, but we also provide a complete API to leverage that and query the generated build. And yeah, we provide the infrastructure to write plugin, but also interestingly, scikit-build-core itself can be a plugin for hatchling or for setup tools. It means you don't have to use setup tool core backend directly. If you already have like a project that's making use of hatchling or setup tools, you can integrate scikit-build and just build like your specific module without having to solely depend on the scikit-build-core backend. Adoption, overall it simplified most of the project from 800 line of complex setup.py to 20 line of CMake. All of the project who converted, they got new platform for free, Windows, PyPy. They also get faster multi-threaded compilation. And some statistics, around 3 million downloads last month, used by a dozen of the 8,000 PyPy packages. A Quart CPP that was mentioned this morning during the keynote is also using it. More than 250 package using scikit-build-core. And then some additional stats. Here we have like some all the link mentioning the stats are available here. And then Henry also wrote an interesting package called PyStat that allows us to get all the data from the entire PyPy and gave her some interesting stats. Here we review some case study. I will skip some of them, but like NVIDIA sort of converted all their project to use scikit-build-core. We also use scikit-build to build the CMake and Ninja wheel, to also build the Clang format wheel. It means we can easily distribute CLI in wheels. And also we can mention that we can build generic wheels that are not specific to a Python version. PyZMQ. What are the key benefits? We have static configuration via PyProject. We can easily set a lot of options. We have cross-platform support, and overall we simplify the build process. And now the key question, how to get started. The platform that was introduced, the website that was presented this morning in the plenary session, scientificpython.org, has a development section. And if you go on that website, you're going to have a link to a cookie cutter or to a template that you can easily generate your project. For example, here I do pipex run cookie cutter and the name of the template. It will ask you a few questions, the name of the project and whatnot. And at the end, the recommended backend for compiled code is going to be scikit-build-core. And then you click enter. Then you get your project. You push it to GitHub. And then out of the bat, you're going to get all of the GitHub actions set up for testing deployments, CI build wheel settings, pre-commit, read the docs ready, Nox files for local development. The icon on the left is also a QR code, and I also have a QR code on the last slide. Some link with resources and some related work that we help make happen. And this weekend at the sprint, yeah, if you want to experience the joy of packaging, come join us, bring your project, and if you are looking to be a contributor, join us. And now, thank you. On the left in the image, we have the contributor of scikit-build-core, around 30 of them, scikit-build classic, 70 of them. And then, yeah, big thank you to my colleague Matt, to Henry, to the attendees. We have two monthly meetings, developer and community. You can get the link from our GitHub. Thank you to the CI Build With team, the CMake team, and the wider community. And yeah, and thanks to NSF for funding the effort. And voila, I'm open the floor for questions.
Thank you, John. We'll take some questions. Yeah.
So I know when it comes to building packages, individual needs fragment very rapidly for the particular weirdness of a package. But there is one that I think I'm probably not alone with, and that's the notion of when you have the Fortran, the C++ packages that are not directly the wheel itself, but an external library that you're bringing in and want to include in part of the distribution of the binary wheel. Being able to specify how they're included in the construction of the wheel, you're nodding your head like you've heard of this before. But the question of how to control this, a nice pattern for doing it. Otherwise, we're forced to look at things like, how does PyTorch do it? How do they do it in some of the NVIDIA packages, but not others? And it's again, a bit scattered. But I wanted to bring up the topic and ask for thoughts or suggestions.
Yeah, there's no bulletproof solution for that. And like, if you can statically build, you go that way. Otherwise, you're going to have your shared libraries, but then the question is like, is there other project depending on these shared libraries or not? And then there's like, you want to avoid symbol clash. Then there's other case where it's like, if you have like already a desktop application that embed Python and you install the wheel, there's a lot of different scenario. Yeah, we are like working on that. We are also like right now working with the folks at NVIDIA, for example, to also streamline to address this type of challenges and deal with like symbol resolution and provide tooling to better understand what's wrong with your wheel. But yeah, no bulletproof solution here, and these are like step in the direction.
Hi, thanks a lot for the talk. Wanted to confirm that I understood something. So let's say that a developer is working on a project using scikit-build-core, and it turns out that CMake or Ninja, the build systems, are installed. Installing the library will retrieve those and install those in the machine of the developer?
Yeah, that's correct. Like we are providing CMake and Ninja wheels that are we are maintaining. And each time there's a new version of this package, they are published on PyPy. It means if on your system you don't have this dependency, it will be automatically downloaded for you. Yeah.
So I'm just curious, are you aware of any reason why somebody who's on scikit-build right now can't migrate to scikit-build-core?
On the documentation, we have like a section called migrate to scikit-build-core that will answer all the questions. But there's few corner cases, and we don't yet have the version 1.0 of scikit-build-core. We want to address these corner cases. And in our current milestone, we have some of these issues, and we are discussing them. And then after we have addressed all of that, we will release scikit-build 1.0. But yeah, there's few like cases where it's not supported yet. And then we will also update scikit-build classic to, under the hood, leverage scikit-build-core. And that way, project, because it takes time, so you can impose a timeline on project. That way, existing project will just work, and then it will also streamline our maintenance. But these are the corner case we are addressing now.
We have one more time for one more question.
Speaking of debugging, and specifically of debugging native code and symbolic information, how easy it is to, when you build packages this way, to then debug that installed package, and are there any standard facilities for this?
Yeah, the way you will go about it, to build your project, you can disable build isolation, and then you have a regular you have a regular project with your Makefile, Ninja file, and then you can just like open your Visual Studio on Windows or your regular debugger, and then you can just like work on your project the way it is. And if you enable the editing mode, the editable mode, then you can easily then run your regular like test that would be written with PyTest and whatnot, and you can like get the best of the two worlds then.
Okay, let's thank Jean-Christophe again for nice talk.